In today's note, we're going to be looking at the motion of the planets. So first thing we're going to look at is rotation. And the rotation is one complete spin of the Earth on its axis. So this is when the spin spins around or rotates once. And so this is what basically causes night and day. So the portion of the Earth that faces the sun experiences day, and the portion of the Earth that faces away from the sun experiences night. So as it completes one rotation, each side is going to experience day and night. One complete spin takes about 23 hours, 56 minutes, and 4 seconds, although we approximate it to 24 hours. So that's where you get your 24-hour cycle for day and night. That's one complete rotation. And you may not know it, but Earth's rotation is slightly slowing over time. So in the past, a day was shorter because the Earth spun faster. But now that it's slowing down, it's gone to around the 24-hour mark. So basically, we just see the Earth rotating here, right? So it's just rotating. It's spinning around its axis. We have the axis would be, say, up and down here. It's kind of glitchy. But the axis is kind of what it's spinning around. A revolution, a revolution is one complete orbit of the Earth around the sun. So you can kind of see here in the small image, the Earth is still spinning around its axis, so we can kind of see. You can kind of see the poles sticking out at either end, so it's spinning around that, but it's also revolving around the sun. And each year journey is considered 1 year, or 365.25 days. So those 0.25, that's what adds up over time. So that's why every 4 years we have a leap year. So those 0.25 adds up until we eventually get one more day, which is the leap year. So rotation is a day, or the Earth spinning around its axis. Revolution is 1 year, where it's spinning around the sun. So again, you can see another example here. You can see some of the kind of key times. We have the Earth spinning around its axis that you can see here. So it spins around as it goes around the sun. Because it's on its axis, certain parts are closer to the sun, which we would have summer. So we can see here, because it's tilted on this angle, these parts like North America and South America are closer to the sun than the other side of the world. So this would be our summer months. And then as we start to continue to go around, our parts get farther and farther away from the sun based on the tilt. And again, over here, we're farther away. This is our winter months. And then we kind of go back into spring where we get closer to. So that's again how we get our seasons, right? Because it's revolving around the Earth, it's tilted on an axis. That tilt determines if we're closer, or to which parts of the Earth, are closer to the sun, and which parts are farther away. If you're closer, you're going to be in your kind of spring and summer months. If you're farther away, it's going to be your fall and winter months. So an equinox is a time of year when day and night are approximately equal. So this would be basically the tilt. The Earth's tilt is perpendicular to the sun, or the angle of sunlight. So the sun hitting the axes is basically a 90-degree angle. So that means the amount of daylight and sun and nighttime are approximately 12 hours each. So you may hear the terms like the vernal equinox or terms like that. So that's basically what it's referring to. Next is phases of the moon. So similar to Earth, the moon also rotates on its axis and revolves around the Earth. And the moon is illuminated by the sun. However, this side does not always face Earth. So the part of the moon that is illuminated, or the part that we can see, doesn't always face Earth. So that means that the amount of moon, or the amount of lit moon we can see, will vary. And that's where we get the phases of the moon. So we can see the moon here, it's rotating around the Earth. We can see that only the one side is getting lit up by the sun. Again, remember, the moon is non-luminous. It doesn't create its own light. And you can see basically based on our view, so that's what this little box or dotted line represents. This is our view of the moon. So this is what we would see. So based on our angle, we would see these different phases, going from a new moon to a full moon and then back. And that's based on what the lit part of the moon that we can see. Some other things that are associated with the motion of planets, we have our solar eclipse. So the solar eclipse is when the moon blocks the sun's light to Earth. So this is when the moon lies directly between the Earth and the sun. So the sun or the moon would get in between the two, and it would create basically a dark spot that would travel across the Earth because there's no sunlight getting into that spot. There was one a few years ago, and this is the big thing where you don't want to stare at the moon or at the sun, even though it's blocked by the moon, because as soon as then it disappears, you get hit with all the sunlight at once, and it could hurt your eyes. A lunar eclipse. A lunar eclipse is when the Earth blocks the sun's light shining on the moon. So this is when the Earth is between the sun and the moon. So this would be where we can't see the moon. So basically the eclipse is when we can't see. Lunar eclipse, we can't see the moon because the sun isn't shining on it to light it up. And the solar eclipse is we can't see the sun because the moon is blocking out that light. Tides. So the tide, in terms of water in the ocean, these are all related to, again, motions of planets. And in particular, the moon. So the moon's gravitational pull generates what we call tidal force. And this causes the Earth, in particular the side closest and the side furthest from the moon, to bulge. So basically they kind of get pulled towards, or if you think of, you have the Earth in a circle, it kind of, the one side gets pulled towards it. And if you imagine pulling a sphere, it's going to stretch both sides, the one closest to and the one furthest to. And we'll see an example of what I mean by this. So these bulges are what causes high tide, and in the middle of the Earth, we have our low tide. And so basically you have 2 high tides a day and 2 low tides, and we'll see in a diagram in the next one of what we mean by that. So here we have our Earth. So this part of the moon is basically pulling, or this gravitational pull is pulling this part out, as well as the side opposite of it. And we can see that even though the other side, there's still a high tide when the exact opposite. So this is kind of what we see of the high and low tide. And this is what we can see by what I mean by the bulge. So the Earth or the moon is here, its gravitational pull is pulling this side out of the Earth. It's not drastic, as you can see here, but this is where we would get the high tide, because this side is being pulled out as well as this opposite side here. So these two sides are bulging out due to the gravitational pull, and in the middle is where you have your low tide, and as the Earth spins around, then the other sides have the high tide, and then they switch basically. So again, that's kind of a more visual representation of what we mean by it bulging out. And here we can see it happening again. So we have the moon here, the Earth rotates. So the moon is in one spot as the Earth spins around the different parts. So this A part is rotating. So the 2 sides are always staying bulged out as the Earth rotates. So this location is now here. So there'd be a low tide, then it goes to a high tide, then low tide, and then back. So again, that's where we kind of get the 2 parts. Again, it's just a brief overview, as long as you're kind of with the understanding that the moon's gravitational pull affects the tides on Earth. So that's what causes our high tide and our low tide. And again, it's just an overview of some of the different motions. So we have the revolutions of the Earth and the moon, and we have the rotation of Earth. And we also have the different phases of the moon, as well as looking at eclipses.